we're ready to rumble here. Okay. So, I was going to make a note about WebAssign, but I think I'll just say it briefly. If you have any technical difficulties with WebAssign, I mean, it goes for all the questions you could have. Oh, great. I don't know if you can hear that, but they're landscaping outside, so they've got that big like. So that should be fun. It's not as bad now, but so if you have any technical difficulties with WebAssign, text me right away. And my number is 250-864-8386. Right, just so that we can get those out of the way. In fact, if you have any questions at all, just text me. I know there is like Ask the Instructor on WebAssign, but the Ask the Instructor just kind of goes and stays in WebAssign, so I don't see those until I log into WebAssign, which is not necessarily every day. Recently, it's been almost every day, but it's not necessarily. So if you want to get a hold of me, you can just text me. And I'd say that's probably the easiest thing to do. Okay. I'll say the, I think it's called Ask the Instructor. Ask the Instructor option works, but I don't check those messages every day. Just so you're aware of what's going on, right? Because if it sent me an email or something, then obviously I would get it right away, but it doesn't, so it's kind of weird. I actually didn't even know it existed until I logged into WebAssign one day and saw a message about a question. So, very funny. Okay. So just as like a not really a review, but more of a summary, I'll call it a review just because of last day, just to jog our memory of what we were doing. We were talking about roots, right? Any root. So we were talking about the properties of the nth root. Things like we can't take the even root of a negative number. We can take the odd root of a negative number. If we're doing roots on our calculator, usually we just take whatever's on the inside to the power of 1 over the root. And that's going to be a kind of a quick trick for dealing with roots. Any root. What else could we do? Oh yeah, we can combine roots if they have the same root. We can split them up as long as we're multiplying or dividing. Right? So those are just properties of the nth root that we talked about. Then we moved on to use the root in rationalizing the denominator. So we talked about rationalizing the denominator. So that's when we figured out a convenient value of 1 to try to remove that root from the denominator, and then ultimately we end up having to put it somewhere, so we have to put it in the numerator, right? But a lot of the time we don't want a root in the denominator, and so we have to be able to move it around, right? And so that's called rationalizing the denominator, or putting it into standard form. Standard form just means no roots in the denominator. a little bit tricky if we had a power inside as well as the root, but we had a way to deal with that. We just need to use that formula that we talked about. So that was all putting things into standard form and rationalizing the denominator. Then we moved on to talk about polynomials. Polynomials, we talked about some terminology around the polynomials. So each chunk of stuff in a polynomial is called a term. Each term has a coefficient and a variable, typically x. And then the highest power of the variable is the degree of the polynomial. And just in general, we write these polynomials in decreasing powers, right? So we have our highest power of x first, and then the second highest, next second highest, next second highest to the lowest, right? And so that's how we typically write polynomials. We talked about adding or subtracting polynomials. Adding and subtracting polynomials, not that bad, right? Usually we'd have to collect like terms and simplify the coefficients, but adding and subtracting polynomials is not that bad. So the tricky part is if we have to multiply polynomials, then, right, we need to expand each of that polynomial, the first polynomial onto each term in the second polynomial, and the third one, as we saw in the special products, which is where we ended. But if we're multiplying polynomials, just as a reminder, right, that's FOIL if you're using just two polynomials with two terms each and you're multiplying them, then you can use FOIL. Otherwise, you just extend that idea a little bit and just take each term and expand it onto the other terms in the other polynomial. And of course, we're going to work a lot with expanding. Today, we're going to get into factoring. So that's kind of doing the reverse of expanding, kind of collecting things. And if you think of an accordion, right, you've got you're expanding, and then factoring is just kind of smushing it up and making it as compact as you possibly can. So we ended on the special product formulas. So if we go to our notes, the ones I posted, the fundamentals part 2, we talked about these special product formulas, and I did give you the heads up that we're going to see these again, but kind of in reverse as the factoring formulas. So if you've scanned ahead in the notes, you'll see the special factoring formulas, but they look exactly the same, right? So one thing that we did, the special product formulas, we don't really need because we can just go through and expand this manually to make a to the 3 minus 3a squared b plus 3ab squared minus b cubed, which is the what we ended on last day. We just went through and did this by hand. So we can use these special product formulas. One thing that I want to emphasize is the special product formulas. Like I said, I would almost prefer it if you just expanded things manually. So we'll do one of these problems together, but then I also want to just expand it manually just so you can see that you end up at the same thing. And it's a little bit more predictable. So I'll cut this whole thing into our notes. Oh, I guess I should denote the end of the review. That's the end. So, there. Which one should we do? Let's do, let's see one that's kind of fun looking. Let's do 40 together. So we're going to use the special product formulas, but then I'm also going to do it just manually, right? So 40. Expand using the special product formula. So I'm kind of changing the question a little bit. Special product formulas. Then expand manually. So we have 2y plus 5 times 2y minus 5. So I've got 2y, I can let that be my a, and 5 be my b, right? And so here I've got a plus b times a minus b, right? If I just let a be 2y and b be 5. Okay. So now if I look at a plus b times a minus b, then if I scroll back, if I steal my special product formulas, and in fact, I'm only going to steal the part I need, save us some space here, I think. Here, a plus b times a minus b, a plus b times a minus b is this first one. So if I'm expanding it out, it's going to simplify to a squared minus b squared. So then what I know is that this, I'll do this, equals a squared minus b squared. And what I'm going to do is I'm just going to scoot this. Where am I going to scoot it here? Let a, there. Okay. So what I'm going to do is, okay, well then, right, my 2y plus 5 times 2y minus 5 is going to be equal to a squared minus b squared, where a is 2y and b is 5. And so 2y plus 5 times 2y minus 5 must be equal to 2y squared minus 5 squared. So are you guys familiar with the triangle of dots as therefore? Right, this is shorthand for therefore. And I'll use that a lot, right? Oh, good. Okay, so if not, it's a really useful shorthand. And so therefore, we can say that, oops, 2y plus 5 times 2y minus 5 must be 2y, and I'm going to put brackets around there just because I have to treat it as one thing, and especially if I'm squaring it, I have to bring that square because I'm multiplying. I have to bring that square onto both of these, both the 2 and the y. So I'm going to put 2y squared minus 5 squared, which is equal to 4y squared minus 25. Notice that, well, this is easy enough to do, right? The problem is being able to remember that a plus b times a minus b is a squared minus b squared, right? That's the problem. Then figuring out what a and b are and just plugging them in, that's easy. So now, now expand manually. Okay. This is the one that I prefer. It's a little bit more work, but I don't have to remember these special products, and that's a nice thing for me. The less I have to memorize, the better. So now, if I have 2y plus 5 times 2y minus 5, I'm going to expand this out. So I've got 2y times 2y, and then 2y times negative 5, so plus 2y times negative 5. Maybe I'll scoot this over so I can have it all on. Whee. Oh, that didn't work, did it? All on one line. So 2y and 2y, notice that I'm kind of speeding up my expanding a little bit. You can speed it up even more, but now I've done 2y times 2y, 2y times negative 5, 5 times 2y, that's my next one, and then so plus 5 times 2y plus 5 times negative 5. Just being careful here, 2y times 2y is 4y squared plus, and then 2y minus times negative 5 is actually minus 10y plus 5 times 2y plus 10y, so those are going to cancel each other out, and then minus 5 times 5 is 25. Bink, bink. So now I've got 4y squared minus 25, which is the exact same thing I found using the special products. And of course, you're hoping that they're going to end up being the same, otherwise you've done something wrong. So it's just two ways of doing the exact same thing, right? We will use this for factoring later, so we're not getting away from memorizing, but if you're expanding, I think it's just easier to just expand things manually. Maybe that's just me, but that's what I think.
I have a question. Sorry.
Sure.
So for grading, would you like us to do the manual thing or the formula would work?
Either way works. If you're using the formula, you'll have to show me like this,
Formula. Yeah.
which one you're using and
Okay.
what the values are, and then you can go straight there if you want.
All right.
Yeah, so as long as you show your work, I'm easy with either one.
Like we can use the formulas and not do the manual expanding, or we can do the manual expanding and not use the formulas, like either way.
Correct. Yeah, that's perfect.
Thank you.
Okay. Okay. Good, good, good. Let's see here. So that's expanding. Let's talk about factoring. So factoring is usually if we have to, or if we want to cancel some terms, or if we want to kind of compress an expression to something smaller or more compact, then we're factoring. So we've got this little diagram here, which I find pretty useful, right? So we've got x squared minus 4. If you factor it, it becomes x minus 2 times x plus 2, right? And then if you're expanding, then you're expanding these brackets and you're getting rid of brackets. So in my mind, factoring is kind of when you make brackets, if that makes sense. And then expanding is when you get rid of brackets, right? You're expanding things and removing brackets. So let's see here. So here, so expanding is when we're removing brackets. Factoring is kind of creating brackets. I'm not going to write that, but it's kind of, you know, smushing things together and making it more compact typically. Okay, so a lot of the time we'll use factoring, like I said, to be able to cancel things and to simplify things. And so sometimes we can use factoring to simplify things. We usually, and there are other uses for factoring, but usually we usually factor to be able to easily cancel a term or terms. So if we just have a look at this example, which already has been factored, right, just to illustrate how the canceling would work, if I have something like x squared minus 4 over x minus 2, there's a lot of illegal math that could happen here, right? One thing you might be tempted by is maybe taking this 2 and canceling it out of 4. But because there is addition and subtraction in here, or just subtraction in this case, we're not allowed to do that. Okay? We can only cancel if we're multiplying up top or in the bottom. And I'll show you what I mean. Okay? So in this case, right, even canceling an x and an x is not allowed. We're going to get something that's similar, but not exactly like we would end up with if we just kind of did some illegal math and got there. So here, we can rewrite x squared minus 4 as x minus 2 times x plus 2. And I'm just using the one that's been given, right? So I'm not expecting you to be there quite yet. Although, if you have a look at x squared minus 4, and then we go and we look at our special product formulas, right? X squared minus 4, well, x squared is or x is our a, and then minus 4, well, 4 is 2 squared. So then we have x squared minus 2 squared. So we've got x plus 2 times x minus 2. So that's what I mean factoring. The factoring formulas are just going to go from the right-hand side over to the left-hand side, kind of creating brackets. So if we've got x squared, x minus 2 times x plus 2 divided by x minus 2, if you think of this as one thing, because x minus 2 is multiplying x plus 2, so it's multiplying everything else, it's a common factor. So then I'm allowed to cancel the x plus, or so the x minus 2 with the x minus 2. So what we get is this cancels with x minus 2. So then we're just at equals x plus 2. So that's a lot nicer looking than x squared minus 4 over x minus 2. They're equivalent, but we wouldn't have been able to get from here to here without factoring that numerator first. So that's why factoring is really useful. Okay. We'll start slow. Start with this first example here. We'll kind of ramp it up. So we've got some examples here. We're going to go through and do the last one. Usually people like it if I just do the last one. in theory, that's the hardest one, right? If you've seen the hardest one, then you can kind of pick away at the easier ones. And so that's usually why I'll just do usually the last one. Sometimes I float around, but whatever tickles my fancy. If we have to factor out the common factor, what we do is we just pull out the lowest common multiple from each of these terms. And especially if we're looking at something like negative 7x to the fourth y squared, 14x to the 3 plus 21x to the xy fourth, y to the fourth. Each of these terms has a coefficient. Each coefficient looks like it's a multiple of 7, so that's really good for us. We'll be able to pull out a common factor of 7. Each has an x to the power of 4, x to the power of 1, x to the power of 1. I should be able to pull out a common factor of just x to the power of 1. And then each has a y, so a y squared, y to the 3, y to the fourth. The lowest power of y is y squared, so I should be able to pull out a y squared. And for the x's and y's, how I manipulate those is, well, it's going to be similar to the coefficients, but what I do is I just rewrite them as the lowest power of x times whatever I need to get to where it looks like that didn't really make sense, so let's write it out. Negative 7x to the fourth y squared plus 14x y to the 3 plus 21x y to the fourth. So to find the common factor, it's just going to be the lowest multiple of each thing, coefficients, x's, y's. So here, each coefficient is a multiple of 7. And just to really illustrate where everything is coming from, I'm going to rewrite everything as a multiple of 7, just to show where everything is going and coming from. Each coefficient is a multiple of 7, so we can write 7 times negative 1, right? Because I'm not going to pull out negative 7. That's going to make dealing with the 14. If I pull out negative 7 from 14, it just makes it a little bit harder to look at. So I'm going to rewrite it as 7 times negative 1, x to the power of 4 y squared plus 7 times 2 xy 3 plus 7 times 3 xy to the fourth. Okay. So now I'm able to pull out this common factor. Pull out the common factor. So what I'm going to do, because 7 is multiplying each of these terms, so what's equivalent to this is pulling out a 7, and then I'm going to use square brackets just to show that this 7 is multiplying each term inside here. Negative 1 x to the fourth y squared plus 2x y to the 3 plus 3x y to the fourth. And just as a little quick check-in, I want to make sure that nothing has changed, right? Just by pulling out this 7, I want to be able to put it back in, multiply it through here, right? The distributive property says that, okay, I have to distribute the 7 onto each of these terms, and then I would be back to where I started. So that's a good thing. That's what I want. So now I'm going to do the same thing with the x's, right? The lowest power of x is just x, right? I've got x to the fourth, x. The lowest power of x is x to the power of 1. So we can write, doing the same thing that I did earlier with the 7, keeping the 7 on the outside for a little bit longer. I've got, what I'm going to do is I'm going to stop writing -1 out here as the coefficient and just have negative. But I've got negative, oops, hey, negative, no, maybe I will do -1 times x to the power of 3. X times x to the power of 3 is x to the power of 4, right? So technically I've got x to the power of 1, but if I'm multiplying the same base, then I add the powers, and that's what I can use to split these guys up. Times y squared plus 2 x to the 1, y to the 3, plus 3x to the 1, y to the 4. So now I've got x to the 1, x to the 1, x to the 1. So now I'm going to pull out the common factor. So I've got 7x to the power of 1, just to illustrate that it is that x to the power of 1. You don't need the power of 1. X to the 1 is just x. Times -1 x to the 3 y squared plus 2y to the 3 plus 3y to the 4th. Now I'm going to do the exact same thing with the y's. I'm going to pick it up a little bit. Y squared, y to the 3. Oh, shoot. Oh, so annoying. I got a phone call, but for some reason it ends my screen sharing. I don't know. But I think we're still good. Sorry about that, guys. Lost the chat too. There it is. Okay. So the lowest power of y is y to the power of 2, right? So I've got y squared, y to the 3, y to the 4th, and so I'm able to rewrite all these as multiples of y to the power of 2. So then the lowest power of y is y to the power of 2. So we can write starting with my 7. 7x to the power of 1 times, so all times -1 x to the power of 3, y to the power of 2 is just y to the power of 2, plus 2y to the power of 2 times y, right, y to the power of 3, plus 3y squared times y squared. Y squared times y squared is y to the 4th, which is what I want. Now I can pull these out. Pull out the common factor. So I get 7x to the power of 1, y squared times negative 1x to the 3 plus 2y plus 3y squared. Of course, you're not going to do all this work every single time. This was just to show you what's going on here, right? In fact, a lot of the time, you'll scan the coefficients, scan the x's, scan the y's, and just pull them all out immediately, right? But I just wanted to show you how you can really break it down and just do it properly. So this becomes 7xy squared times negative x to the 3 plus 2y plus 3y squared. $65. You got it. 65 is y times y minus 6 plus 9 times y minus 6. Y times y minus 6 plus, sorry, I've got it over here. Y times y minus 6 plus 9 times y minus 6. The key here is recognizing that y minus 6 and y minus 6 can be treated as one thing. So that's going to be the ticket here. One thing. Treat as one thing. Okay. So what I can do is, since y minus 6 is multiplying each of these terms, right, I can pull out a common y minus 6. So what I'm going to do is I'm going to have y minus 6, but then y minus 6 is going to multiply y plus 9. Right? So it's definitely weird, but just treat it as one thing. That's going to be the ticket. So you want to scan and see if you can kind of lump things together. Let's do 67 as well. Why not? 67 is 2x squared y minus 6xy squared plus 3xy. So now I'm going to, move a little bit faster. I'm going to scan for my lowest common multiple of the coefficients, the x's as well as the y's. Okay. So what that's going to look like is, okay, I've got 2, negative 6, and 3. I can pull out a common 2. Okay. And I'm just going to write it out, the 2 in front, and then I'll deal with the rest later. And then, so moving on to the x's, I've got x squared, x, and x. So I can pull out a common x. So I've got 2x. For the y's, my lowest power of y is just y to the power of 1. So now I've got 2xy getting pulled out from each of these terms. So from 2x squared y, what's missing is I'd have to multiply that by x in order to get back to 2x squared y. To get back to negative 6xy squared, I would have to multiply by negative 3y. And to get back to, hey, I can't pull out a common 2. Somebody stop me. I can't do that. Can't pull 2 out of 3. Come on. So I can't pull, okay. Somebody stop me. So, why did I think I could pull 2 out of 3? I don't know. But obviously, you run into trouble when you try to actually pull out 2 out of 3 and you can't. So I can't pull out a common factor from the coefficients. I can still pull out an x and I can still pull out a y. That much I know. So then I get times 2x to land back at 2x squared y minus 6y to get back to negative 6xy squared plus 3. Oh. And that's factored. After you've factored something, so just like here, after you've factored something, it's always a really good idea to just expand it back out and just make sure that you get back to where you think or where you started. That's where you should get back to. So after factoring, it is always a good idea to check your work by expanding back out, or expanding the equation by expanding. It's actually an expression. If there's no equal sign, it's an expression, but it doesn't matter. By expanding the expression to make sure you get back to where you started. It's probably good. Runny nose like this, I don't think I'd be allowed on campus to teach you guys, so it's probably good that we're online. Here I can have a runny nose all I want. Just me and the dog. Okay, so what I mean by that is we're just quickly going to take this and expand this out and just make sure that I get back to here. Okay. So I'm going to take xy times 2x minus 6y plus 3 is, and I'm just going to expand it out, 2x times x times y is 2x squared y minus 6xy squared plus 3xy. 2, so now I'm just comparing where I started to this, and they should be the same. 2x squared y minus 6xy squared plus 3xy. Good. Which means my factoring was good. So that's just a quick double check that you can do after factoring, just to make sure that you actually kept your values all the same. You didn't alter them. Okay. Factoring trinomials is the next thing on our list here. I'm just going to make a note that it's kind of a good to know. It's not something that I'm going to test you guys on. So I'm just going to put it here, and then just kind of a good to know. But we won't do any, because they can be kind of brain teasers, and I want to save that for the rest of the factoring. So this stuff is good to know, but won't be tested. At least not like that, right? I will expect you to be able to factor things like this, right? But not using these formulas. I find them kind of tricky to work with. Just as a heads up though, just like we saw earlier where the trick was to treat y minus x as one thing, right? If you just have a scanned through here, if you treat a plus b as one thing, then you've got, and let's say that one thing is x, then you've got 2x squared plus 5x minus 3, which all of a sudden is very reasonable to deal with, right? Same thing here. If you treat 3x plus 2 as one thing, then all of a sudden you've got x squared plus 8x plus 12, which again is a lot easier to deal with. So, but we'll see that later on. And we'll have tricks for factoring, stuff like that. Quadratics. But not until next week. So, let's talk about these special factoring formulas. And yes, they are looking exactly like the special product formulas, just kind of reversed. So these these are going to be very useful to be able to recognize and just kind of know the patterns, right? So they're exactly like the special product formulas, but for factoring, it's going to be a lot easier. So these will be useful to know and recognize. Right? So do the exclamation mark. So if you're able to recognize patterns like this, then you're able to factor it into this kind of difficult thing, right? Even patterns like a squared plus 2ab plus b squared is a plus b squared. So all of a sudden you're able to factor this into something really nice and compact. These two, a plus b squared and a minus b squared, we call them perfect squares, right? Because there's we're able to smush them up into this perfect square, a plus b or a minus b. So, and there's a little note about that in our notes later, so I'll leave it at that for now. Okay. But just being able to recognize these patterns and that they go to these specific other patterns is going to be useful for factoring. There are other factoring tricks too. Let's do a quick example here. We're going to use the special factoring formula. And what we're going to do, which one are we going to do? Oh, which one looks good? I think we should do, did I even do any of these earlier? Trying to remember what I did with other class. Otherwise I confuse myself too much. Let's do 77, just something kind of simple to kick it up, start it off. 9a squared minus 16. Here's the thing. I'm looking at 9a squared minus 16, and I'm looking at these special factoring formulas, and nothing's jumping out at me immediately. However, if I just look at 9a squared, okay, so I've got something squared minus 16. Well, I can rewrite 16 as something squared as well. So then I've got a square minus a square. So what if I have a squared minus b squared? Then I just need to figure out what a is and what b is, and then I'll be able to write it as this difference of squares. So here, I can kind of imagine this as a squared minus b squared, and just as a little note so I don't have to keep scrolling, a squared minus b squared becomes a minus b times a plus b. I just need to figure out what my a and my b are. So if a squared is 9 lowercase a squared, then I can rewrite 9 as 3 squared. Right? And so we do 9a squared minus 16 is 3 squared a squared. By properties of the exponents, right, I'm able to use that, and then minus 4 squared. Right, rewriting 16 as 4 squared. By properties of exponents, I'm allowed to rewrite this as 3a all squared minus 4 squared. So now all of a sudden it's kind of obvious that a is 3 lowercase a and b must be 4. So to try to match here, right, if I'm factoring this thing out, then I can rewrite this as 3a minus 4 times 3a plus 4. And once again, what I'm going to do is I'm just going to multiply this out. So I'm going to expand this thing out just to check my factoring. Because I don't know about you guys, but for me, expanding is fun. It's easy. It's I don't know, it's just my favorite. Factoring, not so much, right? So I don't feel as comfortable factoring. So for me, it's always been, yeah, I think I'm not alone in this, in not liking factoring as much as expanding. And so I'm just gonna check my work, right? So I always just take, so now check your work by expanding. So 3a minus 4 times 3a plus 4 is going to equal 3a times 3a. So I'm going to go a little bit faster here. Puts me at 9a squared. 3a times 4, so plus 12a. Negative 4 times 3a is minus 12a, so those two will cancel. And then minus 4 times plus 4, minus 16. So here, 12a minus 12a goes away. So now I'm at 9a squared minus 16, which is exactly where I wanted to get to. So, whee, good to go. Okay, so, good. So factoring is going to take practice. But the thing with factoring is if you've seen enough of them, then you kind of get to say to the point where you're like, oh, I've seen something like this before and this is how I dealt with it. And that's kind of the basics of problem solving in general. Having been exposed to problems that are similar and applying the same solution, just tweaking it a bit. So, we'll talk a little bit more about these perfect squares. But we did talk about them already. So, just some terminology. A trinomial, remember, is a polynomial with 3 terms. 1, 2, 3 terms. 1, 2, 3 terms. So each of these are trinomials. So a trinomial is a perfect square if it's of the form a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. These are going to be really useful to be able to recognize, especially in terms of factoring, right? And so these will be really useful because it equals a plus b squared or a minus b squared. So what we'll see later, I think it's later, yeah, it is manipulating an expression to maybe make it look like a perfect square. So then we'll be able to leverage these easy factorings. We'll sit on that for till the next example. So we can also factor fractional exponents. So fractional exponents are when we have fractions in the exponent, which we know from last day means that we're taking roots, right? So we've got the nth root is x to the power of 1 over n, so now we've got a fractional exponent, but we're also able to factor those. So let's do an example. I'll show you what I mean. You follow the same rules though. You pull out the lowest common multiple from each of the terms, and that's how you factor it. So, so what we do, even with fractional exponents like this, we can still rewrite them just like we did earlier in rewriting x to the power of 3 as x times x squared, for example, to be able to pull out an x. We do the same thing with fractional exponents, and we just have to be on the lookout for the lowest common exponent, pull it out, and do what we just did earlier. So let's go through 96. So I've got x to the negative 1/2 times x plus 1 all to the 1/2 plus x to the 1/2 times x plus 1 to the negative 1/2. So just kind of scanning this thing, I've got some x and some x plus 1, right? X and x plus 1. So I'm going to be able to pull out some x and some x plus 1 from here, right? I just need to figure out what my my lowest common exponent is. So if I focus on the x to the negative 1/2 and the x to the 1/2, x to the negative 1/2 is smaller than x to the 1/2, right? And so what I'm going to do is I'm going to pull out a common x to the negative 1/2. Pull out, oops, a common x to the negative 1/2. A little bit trickier than just pulling out an x from x to the 3, right? But the same idea applies. So the x to the negative 1/2, oops, that's just going to get pulled out. What I need to alter and rewrite is the x to the 1/2. X to the 1/2 is essentially x to the 1 minus a half, right? Which is where this 1/2, negative 1/2 comes from. So this becomes x to the negative 1/2 times x plus 1 to the 1/2 plus x to the power of 1 minus 1/2 times x plus 1 to the negative 1/2. remembering that if we've got adding or subtracting up here in the exponent, then I'm multiplying the same base down here. So what I can do is I can rewrite this as, and I'll just put a little underline here to show that that's what's changing right now. X to the negative 1/2 times x plus 1 to the 1/2 plus x to the 1 times x to the negative 1/2. So now all of a sudden we've got that common multiple times x plus 1 to the negative 1/2. So now I'm able to pull this out here and here. So this becomes x to the negative 1/2 times x plus 1, to the 1/2 plus x times x plus 1 to the negative 1/2. So I've pulled out the lowest power of x. Now I'm going to do the exact same thing with x plus 1, treating x plus 1 as one thing. So now, comparing these two, right, x plus 1 to the positive 1/2 or x plus 1 to the negative 1/2, I'm going to be able to pull out a negative 1/2 again, right, because that's my smallest exponent. And so I'm going to pull out a common x plus 1 to the negative 1/2. And I'm going to use the exact same trick that I just used. Right? So I'm going to rewrite this as x to the negative 1/2 times x plus 1 to the power of 1 minus 1/2, right, for now. Plus x times x plus 1 to the negative 1/2. That's not changing. But, and I'll just kind of underline it to show that that's the one that's changing right now. I can rewrite x plus 1 to the power of 1 minus 1/2 as x plus 1 to the power of 1 times x plus 1 to the power of negative 1/2. So we get x to the negative 1/2 times x plus 1 to the power of 1 times x plus 1 to the negative 1/2 plus x, and then nothing changes over here, x times x plus 1 to the negative 1/2. Now I can pull out this common value of x plus 1 to the negative 1/2, x plus 1 to the negative 1/2. I can pull that to the outside. So I end up at x to the negative 1/2 times x plus 1 to the negative 1/2, all times x plus 1 to the power of 1 plus x, after pulling out those common factors. So we're almost there. We can simplify this a little bit, right? Looking at these exponents, they're the same, right? So what I can do to make this look a little bit cleaner is I can combine those bases, right? And just kind of pull out the exponent, the common exponent. And so that's going to look like x times x plus 1 all to the negative 1/2. Right? I'm allowed to do that because I'm multiplying. Times, and then x plus 1 to the power of 1 is just x plus 1. So let's just kind of ignore that for a little bit. X plus 1 plus x is 2x plus 1. Last thing I can do if I want to is I can expand the x times x plus 1 to make 2x plus x. And that might make it look a little bit cleaner here. 2x plus x to the power of -1/2. And then I'll substitute square brackets for round brackets just so it's not so jarring. 2x plus 1. And that's it. So this would be completely factored. Completely factored. Or factored completely. Okay, good. Right, so dealing with those fractions and the exponents, it's a little bit harder, but same methodology, right? You split them up because that's how exponents behave. So there are a ton of practice problems, but I want to just do the last one here. Whee. And then I'm pretty sure I have the solution somewhere. So, and I said that I would find them last day, and then I found some, but not all of them. So I'll put them together and post them for you guys so that you can practice these if you want to. So we want to factor all of these completely, and we're going to do 126 together, because why not? Yeah. So this one is going to incorporate the special factoring formulas, sort of. So this is what I mean by it's really useful to be able to recognize that sort of pattern and then tweak it a little bit to make your factoring a lot easier. So let's do 126 down here. I've got a squared plus 2a squared. A squared plus 2a all squared minus 2 times a squared plus 2a minus 3. So what I'll do is I'll just make a note here that if we let this be a, right, I've essentially got a squared minus 2a minus 3. We basically have a squared, capital A squared, minus 2a minus 3. That's not a special factoring formula, but it's good to be able to recognize that I've got this kind of pattern that's close, right? So if we look at our, where are our special factoring formulas? Just going to steal what we need. We don't need the names yet, or right now. So if we look at these patterns, right, I've got a squared minus b squared. So a squared minus 2a minus 3 doesn't really look like a squared minus b squared because I've got this minus 2a. So that's okay, I'm just going to skip to the next one. I've got a squared plus 2ab plus b squared. Okay, fine, close. But I'm going to opt for this next one instead, a squared minus 2ab plus b squared. I can easily rewrite that as a minus b squared as long as I can get this, this latter half of the expression to kind of look like b plus b squared, right? 2ab plus b squared. the a to the 3, b to the 3, I don't have anything to the power of 3, so they're out, right? And so this is why these perfect squares are good to kind of recognize, right? Because that's basically what I have going on here. So what's missing is, so we basically have a squared minus 2a minus 3, which we can, I'll say, morph to look like a squared minus 2ab minus, is it minus b squared? Plus b squared. Plus b squared, which we can rewrite as a minus b all squared. Oh yeah, so the b is the tricky part, and that's the part that we're gonna kind of work on. So it's not quite 3, but there's a trick that we're gonna do. So the hard part that we're seeing, right, is we have to have minus 2ab, but we've already got minus 2a, so that means that b must be 1, right? In order for this to kind of work out, b must be 1. Okay? So in our example, we see b must be 1, right? So, okay, so if we let b equal 1, then I've got a squared minus 2a, b is 1, and then plus b squared, but plus b squared is really just plus 1 squared, which is just plus 1, but I've got minus 3 here. So how do I deal with that? It's very similar to the exponents. What I'm going to do is I'm going to rewrite negative 3 as 1 squared minus 4. Okay? So if b equals 1, we need to rewrite negative 3 as a function of b squared, which is 1 squared. So what I can do is I can say, well, negative 3 is the same as 1 squared minus 4. And so I'll say, notice, negative 3 is 1 squared minus 4. So I can do that, right? 1 squared, that's the b squared. So now what I have, I'm just looking at if I should use the big nasties or if I should just stick to the a's for a little bit. I think I'll keep the a's. So now I have a squared minus 2ab. Oh, so how did we know that b has to be 1? Okay. Because when I'm looking here at my original equation, then I've got, so I'm making this a squared plus 2ab capital A. So then I've got a squared minus 2 and then a, but really what I need is to have minus 2ab for this to all work. And so what I know is in order for this to stay the same, b has to be 1. So I don't have a choice about what b is because this has to stay the same and this is all part of a. And so I have to just multiply it by 1 and that's why b must be 1. So help. So we'll keep going a little bit. If that's not helpful, then just let me know in the chat. So yeah, definitely gonna take some practice, right? Just being able to recognize these things and figure out what you need and kind of tweaking it. For me, the hardest part is looking at this and saying, oh, well, I can rewrite -3 as 1 squared minus 4, and then I'm done. So what I have is I have a squared minus 2ab plus b squared minus 4, right? Because what I have, right, is this is my b squared here is 1 squared. So let a be the a squared plus 2a, and b be 1, right? What I can do is now this is going to be its own thing, and then I'm going to subtract 4. So what I've got is I've got a squared plus 2a squared. So that's where I started. Minus 2 times a squared plus 2a, technically times 1, right? That's my b, plus 1 squared minus 4. Just convince yourself that that's exactly what we were looking at, right? Especially if you put brackets around here. 1 squared minus 4 is -3, so then it would be -3. But instead, what I'm going to do to make my factoring easier is I'm going to group this whole kit and caboodle and make it a minus b squared and then -4. So here this becomes equals a, which is a squared plus 2a, minus b, which is 1 squared, and then -4. Yeah. I can simplify this a little bit because I'm adding and subtracting in here. I don't need these brackets. So then I have a squared plus 2a minus 1 squared minus 4. A little bit tricky. So we can label both of the a's the same. Yeah, so here, if we go back up here, I'm saying that a squared plus 2a, so that's inside the brackets, is a. Yeah. So then this whole term is a squared, and then this would be minus 2a because it's not squared. Cool. Cool, cool, cool. All right. Awesome. A little bit easier is if you're able to group terms. So just like we kind of did here, where I said, oh, okay, I'm going to create a group here, a convenient group, and then I know how to factor that, and then I'll just tack on this -4 on the end, right? So if we go to the next section, it's a little bit more fun. It only works, and I'll highlight it too, but if you have more than 4 terms, so something really large that you have to factor. But it's a nice kind of trick to have. So polynomials with at least 4 terms, so it has to have at least 4 things in it, 1, 2, 3, 4. Right? So it won't work otherwise, but it is a nice trick. We can sometimes factor by grouping the terms. So what that means is if you have something like x to the 3 plus x squared plus 4x plus 4, what you can do, because you're just adding across here, you can put brackets in and it won't change anything. But if it makes it easier to pull out a common factor of x squared, for example, and a common factor of 4, then you've got this x plus 1 and x plus 1 as a common factor of each of these terms. So now you're able to pull out a common x plus 1 and multiply that by x squared plus 4. So let's just do a little example. Let's do 86. So if we have 3x to the 3 minus x squared plus 6x minus 2. I've got 4 terms, so that's good. So I'm going to try grouping them because it's easier. There are a couple of different options, right? 6 is a multiple of 3, right? So I could lump those together and just kind of try to pull out 3x from those. But then I'm left with x squared and 2, which is fine. Maybe that's fine. Another thing is I could just do exactly what we did up here and just say, okay, I'm going to put these x to the 3 and x squared together, and then the 6x minus 2 on its own. Either way, we're going to end up at the same answer. So this becomes 3x to the 3 minus x squared plus 6x minus 2. So what's going to happen here is I'm going to see what I can pull out from each of these. So here I pull out x squared and I end up with 3x minus 1 plus, from 6x minus 2, I can really only pull out 2, right? 2 times 3x minus 1, but lucky for me, I've got 3x minus 1, 3x minus 1, so this is that same trick that we saw earlier, right? These are common factors. So I can pull out the 3x minus 1, so I get 3x minus 1 times x squared plus 2. Or let's try it another way, right? Because there are multiple ways that we can do it, so I don't want you to think that there's only one way. You can kind of try a couple of different ways. Or if you have 3x to the 3 minus x squared plus 6x minus 2, I'll just start with the same equation. What if I decided I'm going to lump together my 3x to the 3 and my 6x? So I can rewrite this as 3x to the 3 plus 6x minus x squared minus 2. Now I'm going to put brackets around here. I'm going to be careful with my brackets around the negative x squared minus 2 because it might be nice to just pull out a common negative, right? But then this becomes 3x to the 3 plus 6x minus x squared plus 2. So then, now from this first term, so there's nothing I can do more in the second term, but in this first group, I can pull out a common 3x, right? So I get 3x times x squared plus 2 minus x squared plus 2. You'll see, very convenient. A common factor of x squared plus 2, which I can pull outside. So now I have x squared plus 2 outside times 3x minus 1. Remember, if you've got a minus here, it's technically 1 minus 1 times x squared plus 2. So you don't want to forget about that because it's just a little placeholder for when you expand this out again. Right? So you don't want to forget about that one. But if I look at these, 3x minus 1, 3x minus 1, x squared plus 2, x squared plus 2, I end up at the same place, regardless of which root I take. And I don't think any other options will give me anything factored, right? Anything kind of smushed together more. Okay. So that's good. Good, good, good. How are we doing? Time. Let's get into 1.4 and then, oh, can we go back? Oh yeah. The last example, this one or this one? I'm guessing this one, yeah. Okay, I'll keep it on the screen for a little bit. So that's factoring. Like I said, it's really just putting it all on you guys and practicing. But I'll do my part and post the solutions. Oh yeah, so what are we doing over here with the green brackets from the previous example? I'm just lumping these together to make them look like this, a squared minus 2ab plus b squared. And I'm allowed to put brackets wherever I want because I'm just adding and subtracting, right? As long as I'm not splitting up multiplication. So this inside the light blue brackets became what's inside the green brackets. Good. All right. So, good. Let's start 1.4. So 1.4 is rational expression. So 1.4 is on rational expressions, which means we're going to be dealing with fractions. Oh, hey. Okay. It glitched out. Okay. 1.4 rational expressions. Okay. Rational expressions are just anything where you've got some sort of, often a polynomial, either in the numerator or in the denominator, or a lot of the time both. There are some things, so a rational expression is a fractional expression. So let's just, because we're going to be talking about fractions, I know I've emphasized it before, but a fraction is a numerator over a denominator. So we need to know that terminology just because denominator, because otherwise it makes it really hard to explain. So a rational expression is a fractional expression, so a fraction, where both the numerator and the denominator are polynomials. So let's have a look here. 2x, that's a polynomial, it's a monomial, it's just one term. X minus 1 is a polynomial, y minus 2 is a polynomial, y squared plus 4. All of these are polynomials until we get to the square root of x squared plus 1. That's no longer a polynomial. It's the square root of a polynomial, but itself is not a polynomial. So but that's okay, we'll be able to deal with that too. So as soon as we're introducing fractions, right, one key thing to remember is that we can't divide by 0. And another thing we have to remember is that we can't take the square root of a negative number, right? And so now these things are all going to be called the domain. So the domain is just all the possible inputs, and usually we just highlight the inputs that we can't have. Let's do this. So the domain is essentially a list of all the numbers, a list of all possible inputs. Which are often values of x. But as we'll see, the variable isn't necessarily x. It can be y, it can be t, it can be s. So, but just in general, we talk about x. And so it's a list of all the possible inputs, or if it's easier, the inputs that yield illegal math. The inputs that yield illegal math. For now, illegal math is dividing by 0 and taking the square root of a negative number, or even the even root of a negative number, but we're going to focus on the square root. So dividing by 0, or taking the square root of a negative number. Can summarize these things with this little box here. Okay, and we use set builder notation. So if we have something like 1 over x, well, we can't divide by 0. So what we say is the domain is the set of all x's such that, remember how we read set builder notation? The set of all x's such that x is not equal to 0. Right? So it can be anything except 0. So here, can't divide by 0. Oops, dividing by 0. The next one, the root of x. Well, the root, if we just take the square root of x, it's the domain of that is the set of all x's such that x is greater than or equal to 0. We're allowed to take the square root of 0, but nothing less than 0. Right? The square root of 0 is 0. Can't take the square root of a negative number. And here, what we're going to find is a lot of the time there are going to be domains. So a couple of different constraints on our domains. The overall domain is the overlap of the 2 or 3 or 4 constraints. And so in this last one, if you have 1 over root x, the first constraint is, well, root x can't be 0, right? But also, because I can't divide by 0, right? So that's this expression here. But then I know I can't take the root of a negative number. And so then here, the domain is the set of x's such that x is greater than 0. So we can't have the root of 0 down there in the denominator anymore. So it's a combination of the two above. Okay. So we are going to be dealing a lot with the domain. So get started here. Let's do some examples. Oh, and I wanted to make a note, so I'll put it kind of down a little bit. So the overall domain will be the overlap of all the individual domains, right? And so you'll see what I mean, but just so you know, the overall domain will be the overlap of all the individual domains. You'll see what I mean in just a sec. So if we kind of go through, we'll start with 7. 7, well, there are no restrictions on 7. The reason is there's no division, right? There's no division happening, so there's no restrictions there, and there's also no square roots. So no division and no roots, therefore no restrictions on the domain. No restrictions on the domain. So how we write this is we say that the domain is the set of x's such that x is in the set of real numbers. And that's kind of a standard blurb, right? So the domain is the set of all x's, of all x, such that x is in the set of real numbers. And this is kind of where we started, but that was, what, 2 weeks ago? Set of real numbers. Maybe it was only 1 week ago. Anyways. Just remembering that notation. So if there are no restrictions on the domain, then that's how we say it, right? So this is going to be a pretty common one, pretty common domain to have. So just get used to seeing it. If we go on to 9, right? Because notice that 8 looks the same. 9 looks the same as 10. 11 and 12 are a little bit different, but let's have a look at 9. So in 9, I've got x squared minus 1 over x minus 3. Okay? Because there's division, right? X minus 3 cannot be 0. X minus 3 cannot equal 0. I can do kind of normal algebra around this inequality. We'll deal more with inequalities. So for now, we're just able to treat these inequalities as if they're equal signs. So then if we add 3 to both sides, I get x cannot be equal to positive 3. And you can just check it. 3 minus 3 is 0. That's not allowed. And so x equal to or x can't be 3 in the domain. So what we say is the domain is the set of x's such that x is not equal to 3. Right? And then it's implied that it's all real numbers except if x is equal to 3. Then I have to pull that out. Right, same idea for 10. Let's have a look at 11. So 11, now I've got a square root. I've got the root of x plus 3. The condition is, well, I can't take the square root of a negative number. And so here, x plus 3 has to be greater than or equal to 0. And like I said, for now, we'll just be able to treat these inequalities as if they're equal signs. So x is greater than or equal to negative 3. If you try values, right, negative 3 puts me at 0. The square root of 0 is allowed. If I do x is 0, that's less than negative 3, right? So it's not in the domain. Then I get 0 plus 3. Negative 3, not 3. If I do negative 4, right? If I let x be negative 4, what I should get is illegal math here, right? So negative 4 plus 3 is negative 1, so the square root of negative 1 is illegal math, so I'm not allowed to do that. It yields it's the imaginary number, but we're not going to go down that road. Okay. So then the domain here is the set of x's such that x is greater than or equal to negative 3. Notice that I'm always checking my domain just to make sure that what I'm saying makes sense. How about let's do 14 just to finish things off here. 2x, because I know I'm out of time or running out of time here. Now I've got a combination, or maybe that's a good place to start our review next day, because I am out of time. All right, I'll leave it for the review next day, but you can give it a go. In fact, maybe give all of these a go and can see how they are. Are there any questions before I let you guys go? No? I'm not seeing any, so I'm going to stop the recording